Okay, so yesterday we were talking about the basic characteristics of polynomial functions. Today we're going to look a little bit more into the nitty-gritty of how these things work. We're going to look at the insides and the details. So we're going to be factoring polynomials mostly. We'll also talk about modeling polynomials, which is writing equations for polynomial functions given the correct information. So when we talk about factoring, there's four patterns that we're going to recognize in this section for factoring polynomials. Synthetic division is something we're going to cover a little later for when these patterns fail us. So the first thing we're going to look for is greatest common factor, GCF. Whether you find one of those or not, the other patterns that we're looking for are quadratic or quadratic form. Difference of two squares and sum and difference of two cubes. And we'll see those throughout the presentation. We're going to also talk about dealing with repeated zeros and what that does to the graph of the function. We're going to talk about writing a polynomial equation given its zeros, and we're going to talk about using electronic tools to model data using regression. You can do this on the TI-84. I'm kind of assuming you have one of those. Desmos, which is an online tool, will do it as well. So as far as factoring polynomials, you always want to start by looking for a greatest common factor. Sometimes that'll just be a number, and sometimes it'll be just a variable, sometimes it's both. In this first example, because the front has a coefficient of 1 is the greatest common factor, it's the constant part of the greatest common factor. There's also an x in every term, though, so we can factor out that x. Now what's left behind, x squared plus 5x plus 4, that's quadratic. It's straight up quadratic, which you've been factoring since Algebra 1, hopefully. So to factor a quadratic, we're going to assume that this trinomial here is actually the product of two binomials, and we need to find them. When you multiply binomials together, you FOIL. So the first term here, the x squared, is a product of the first two parts of our binomial. And then the middle, 5x, is actually the sum of the outers and inners. Most of the time with two linear binomial factors, the outers and inners will be like terms, and so you'll add them together. And then the 4 on the end there is the product of the last two terms. So thinking about the front, to make x squared, the most likely option is to multiply x times x. So we'll put those in the front. To get 4, the first thing that occurs to me is 2 times 2 makes 4. Once we've done that, we need to check to make sure our outers and inners match up. Unfortunately, if you FOIL this, you'll get x squared plus 2x, which does not make 5x in the middle. So 2 times 2 doesn't work. Instead, what we want to do is figure out what else multiplies to 4, and the only other thing that multiplies to 4, as far as whole numbers anyway, is 1 times 4. So when we check our outers and inners here, we have 4x and 1x, which does make 5x. So this is the correct factorization. X times x plus 4 times x plus 1. Now these are the factors, which means we have factored. Normally when we factor, what we're actually looking for are zeros, or the x-intercepts of the graph. Hopefully you remember that each factor corresponds with 1, 0. So the x in front, to make that one 0, you'd stick in 0. X plus 4 has the 0, x equals negative 4. And x plus 1 has the 0, x equals negative 1. So what that means for our graph is that those are going to be the x-intercepts. Right. Dealing with repeated zeros is next. Here's my second example. 2x to the 5th minus 16x cubed plus 32x. Now in this case, I do have a x as part of my greatest common factor, but the coefficients are also all even, so I can factor out 2x, not just x. What's left behind is not quadratic, but it's in something we call quadratic form. Because x to the 4th is the square of x squared, and the 16 has no variables, we can factor this the same way we would a quadratic. The only real difference is that the x's in front are x squared and x squared instead of just regular x. So x to the 4th is a product of x squared and x squared, 16 is the product of 4 and 4 or 8 and 2. The fact that we have a negative 8 in the middle means we should use negative 4 and negative 4, which add to negative 8 and multiply to positive 16. These two factors are the same, you may have noticed, so I could write them as a factor squared, but since they're not linear yet, what I'm going to do instead is factor them. These are differences of squares. X squared is a square, 4 is a square. So this is a difference of two squares, which you should remember is you factor by finding the square roots, x and 2, and doing one with plus and one with minus. We need that for each of these. So the first one factors to x minus 2x plus 2, and the second one also factors to x minus 2x plus 2, and we end up with a total of 5 factors. We can arrange them by their squares. These are what we call repeated factors. They're the ones that produce repeated zeros. X minus 2 occurs twice, and x plus 2 occurs twice. So their zeros, at positive 2 and negative 2 respectively, are repeated zeros. As far as what that does to the graph, you'll see that x equals 0, which was our 0 that was not repeated, looks pretty typical. The graph crosses right through. But the plus or minus 2 zeros over there, the graph touches the axis, but then goes back in to its original side. It doesn't cross. There's no sign change. If it's negative, it stays negative. If it's positive, it stays positive. And that is typical for zeros that are repeated twice. In fact, zeros with an odd multiplicity, that is, that occur an odd number of times, are going to cross, like the one in the middle. 1 is an odd number. So the x equals 0 crosses right through there. And the ones with even multiplicity, like 2, 4, or 6, are going to touch but not cross the axis. Here's our second example. I factored this one for you just to save time. We've got x squared, which means x equals 0 has a multiplicity of 2. X minus 3, so the 0 at x equals 3 has a multiplicity of 3. And x plus 2, so the 0 at negative 2 has a multiplicity of 1. When I need to graph such a so as we look, we can see, first of all, I should point out that x squared, and then the second one is cubed. That adds up to 5, and then if you add the last factor, this we're expecting to be degree 6, so it shouldn't surprise us the end behavior is even. That is, it's up on both sides. Also, the x squared is the even multiplicity 0, so it's where we're going to bounce off the axis. And then at x equals negative 2, we're crossing, and at x equals positive 3, we are crossing again. I'll also take this second to point out, although I won't be looking for this when I grade, the 0 at negative 2, as it comes through, its multiplicity 1, it looks sort of like a line as it crosses through. Here at 0, where we're bouncing off the axis, if you look at this shape right here, it's vaguely parabolic, which is actually a result of the fact that this is x squared. And then over here, where it crosses at x equals 3, it doesn't look the same as the one at negative 2. It wiggles here in the middle, and it looks vaguely cubic, which should come as no surprise because it's a 3 repeated 0. It's a multiplicity of 3. So the shape around the 0 is going to match the multiplicity, the degree of the multiplicity. So line, parabola, cubic. That can make your graphs look a little closer to how they actually are. I won't be looking for that when I grade these. It's just something for you to keep in mind. Let's do another repeated zeros example. This time I need to hit sum of cubes because it was in the outline. So I'm going to start with x to the 5th plus 8x squared. The greatest common factor here is x squared. Oh, I'm going to sketch the graph. Yes. So end behavior first. This is a 5th degree polynomial, so I'm expecting, and the leading coefficient is positive, so I'm expecting it to go up on the right. As x approaches infinity, the function will be approaching positive infinity. And as x approaches negative infinity, since this is odd, it's going to go the other way on the left, or down. So as x approaches negative infinity, f of x will also approach negative infinity. Then I can try to factor to find my zeros. X squared is the greatest common factor. Now x cubed and 8 are both cubes, so this is a sum of 2 cubes. And the formula for factoring you may not have remembered from Algebra 2, but there it is. The trick to using this is to recognize what a and b are. In this case, a is x, because when you cube it, you get x cubed, and b is 2, because 2 cubed is 8. So the correct factorization is x plus 2 times x squared minus 2 times x plus 2 squared, which is 4. This trinomial here on the end is never going to have zeros. The two, or I should say real zeros. The two zeros for this trinomial are imaginary. So they're not going to produce x-intercepts. So the only two x-intercepts we have to worry about for this graph are at x equals 0 and x equals negative 2. The one at 0 is multiplicity 2, so it's not going to cross. But the one at negative 2 will cross. So we have our end behavior coming from negative infinity. We're going to cross at negative 2. We're going to bounce at 0. And then we're going to head toward positive infinity. As far as writing a polynomial, this is basically the same thing we've been doing, but we're going to do it in reverse. So rather than factoring the equation in order to determine where its zeros are, we're going to look at where the zeros are and build the factors from them. So the zeros, first I'm going to look at the end behavior. I note that it's up on both sides, so I'm expecting an even degree. Also, if I look, there's 3 real zeros, actually, although the negative 1, since it bounces off the axis there, is repeated. I should count it twice, which makes a total of 4. Also, I can count 3 turns, here, here, and here. The graph turns, which requires at least 4th degree. Everything seems to point to a 4th degree polynomial. Looking at the zeros themselves, negative 1 has a multiplicity of 2. 2 and 4 each have a multiplicity of 1, which adds up to my 4. So the 0 at x equals negative 1 suggests a factor of x plus 1. Since it's multiplicity 2, I'm going to add it twice. I'm going to square it. X equals 2 means x minus 2, and x equals 4 gives you x minus 4, which is actually all the factors I need for my polynomial. If I have a point that's not a 0 somewhere on my polynomial, I can determine the leading coefficient in case it's not 1. If none is given, we can just assume the leading coefficient is 1, which happened in this case. As far as using regression to produce a model, you should know how to do this on an electronic tool. Like I said, a TI-84 calculator will do it. If I'm staying at my computer, I'm as likely to use Desmos, which is an online graphing tool. The new part about doing regression on the calculator is we're doing polynomial regression now. Rather than being told which degree we should be looking for, this year you are expected to look at the points on the graph, determine which type of polynomial is most suitable. Usually you do that by counting the turns, looking at the curvature. So if we look at this graph, the graph seems to be increasing here, and then it turns and goes back down. So that's one turn, and it seems down here it's probably turning back up. So that would be 2 turns, which means we need a 3rd degree polynomial. If I run a 3rd degree polynomial regression, cubic regression, I find here that the R value, 0.99, that's pretty good. That's close to 1 is very good. So I can use their values for my coefficients. And this is, even if you inspect the graph here, that looks like a pretty good fit for these points. You may end up doing linear regression or quadratic regression, cubic, quartic. The TI-84 doesn't go past quartic, I don't think. So you can expect between 1st and 4th degree for these. That's the last thing I needed to cover. Hopefully this will get you started. Please feel free to ask if you have any questions.